Hello everyone. In this video, I will be presenting on the topic elementary properties of group, and we will try to solve two problems based on it. Under elementary properties of groups, the first one is groupoid. A non-empty set G equipped with one binary operation star is called groupoid. That is, G is a groupoid if G is closed for star. It is denoted by G star. Let us see what does it mean by close. Suppose we have a set of natural numbers, say n equal to 1, 2, 3, 4, and let's take out two natural number from the set, say 3 and 4 belongs to n, and if we apply addition operation to it, the end result will be a natural number itself, so it is closed in this case. Now if we apply multiplication operation to it, even in this case it will be closed. If we take any number from the set of natural number and add or multiply, it gives natural number again, then it means that it is closed. Now let's see for subtraction operation. In this case, the end result is 1, and minus 1 is not in the set of natural number, so it is not closed in this case. Now let us see for the set of integer. We know that the set of integer is given by z equal to 1, 2, 3, 4, 0, minus 1, minus 2, minus 3, and so on. If we take out two numbers, say minus 2 and 3 belongs to z, and apply addition operation to it, we see that the end result is integer itself, so it satisfies the closed property. Now let's see for multiplication operation. Even in this case, the end result is an integer itself, so even in this case it satisfies the closed property. But for division operation, it is not an integer, so in this case it is not closed. Close means that if any operation close means that if we apply any operation on a set, say two number, and it comes under the set, then it is called close. If a set satisfies this property, then it is called groupoid, or it is also called as quasi-group. This is the basic concept of groupoid. Now let us see for semigroup. An algebraic structure G star is called a semigroup if the binary operation star satisfies the associative property, that is this property. If it satisfies this property, it is called as semigroup. Now suppose a set satisfy the closed property and also satisfy the associative property, then it is called as semigroup. Based on it, let us look at some of the examples. Suppose we have a set of natural numbers, say n equal to 1, 2, 3, 4. If we take out three numbers, say 2, 4, and 7 belongs to n, and if we apply addition operation to it, 2 plus 4 plus 7 equal to 2 plus 4 plus 7. In this case, both left hand side and right hand side are equal, so it satisfies the associative property. Now let us see for multiplication operation. 2 into 4 into 7 equal to 2 into 4 into 7. Even in this case, it satisfies the associative property. Now let us see for subtraction operation. 2 minus 4 minus 7 equal to 2 minus over 7 4 minus 7. In this case, the left hand side and right hand side are not equal and it does not satisfy the associative property. The algebraic structure, wait, let me erase this one first. The algebraic structure n plus z plus, that is the set of integer z into q is for rational number, are semigroups, but the structure z minus is not so because subtraction minus is not associative. If a set is closed and also satisfy the associative property, then it is called as semigroup. I hope that is clear. Now let us see for monoid. A set should satisfy the closed property and it should also satisfy the associative property. And if there exists an identity element, then it is called as monoid. A semigroup G is called monoid if there exists an identity element E in G such that E star A equal to A star E equal to A such that A belongs to G. We have a set of natural number that is given by n equal to 1, 2, 3, ... Let us see for addition operation first. See, if we take 2 from the set of natural number, we have to think of an element that should be added to 2 in order to get 2. So in this case, if we add 0 to it, we will get 2. But 0 is not there in the set of natural number. So for addition operation, there is no identity element. Now let us see in the case of multiplication. 2 equal to 2. If we multiply with 1, we will get 2. So, and 1 is there in the set of natural number. So 1 is the multiplicative identity element. We can even see here the semigroup n into is a monoid because 1 is the identity for the multiplication, but the semigroup n plus is not because 0 is the identity for addition, is not in n. Now let us look at the definition of a group. An algebraic structure of set G and a binary operation star defined in G, that is G star, is called a group if star satisfy the following postulates. That is the closure property. We have seen that the associative property, the existence of identity element. The extra thing out here is the existence of inverse element. Let's understand what does that mean. Let us see for addition and multiplication. Suppose we take 2. We know that the identity element of addition is 0 and the identity element of multiplication is 1. So we have to think of an element that should be added to 2 in order to get the identity element 0. So in this case, if we put minus 2, we are getting 0. So minus 2 is the inverse element. Even out here, if we put 1 by 2, we are getting 1. So 1 by 2 is the multiplicative inverse. To sum up, if a set satisfies the closure property, associative property, and there exists an identity element, and there exists an inverse element. If it satisfies all these conditions, it is called as a group. The next one is abelian group or commutative property. If a group satisfies the above given if a set satisfies the above given condition, it is called a group. And if that group satisfies this property, that is A into A star B equal to B star C, such that A B belongs to G, it is called as abelian group or commutative group. A group G star is said to be abelian or commutative if star is commutative. I hope that is clear. The next one is finite and infinite groups. A group G star is said to be finite if its underlying set G is a finite set, and a group which is not finite is called infinite group. That is clear enough. The next one is order of a group. The number of elements in a finite group is called the order of the group. It is denoted by OG or G modulus. If G star is a finite group, then it is said to be infinite group. Now let us look at some of the examples. The first one is show that the set of in a group also it should be integer so that the set of integer forms an abelian group under addition. We let G equal to 0 plus minus. We usually denote set of integer as Z 0 1 2 3 minus 1 minus 2 minus 3 dot, dot, dot. But out here we are using G, so let's just denote the set of integer as G. The first one is the closure property. Let A B belongs to G, A plus B belongs to G. Say let's take 2 plus 3. The end product will obviously give a set of integer, so it satisfies the closure property. The next one is the associative property. Let A B C belongs to G. Say let's just take 4 plus 5 plus 6 equal to 4 plus 5 plus 6. Both left hand side and right hand side are equal to each other, and thus it satisfies the associative property. The next one is the identity element. Let A belongs to G and 0 be the identity. We know that for addition, the identity element is 0. So 0, suppose if we take 2, anything added to 0 will obviously get the same number. So out here the identity element exists. Next one is the existence of inverse. This is the inverse element. For addition, we know that the identity element is 0. So suppose we take 1. The set of integer is given by Z G equal to 0 1 2 3 minus 1 minus 2 minus 3. If we take 1 from the set of integer, we have to think of an integer that should be added to 1 in order to get the identity element 0. So out here, if we use minus 1, we are obviously getting 0. So even inverse element exists. The next one is the commutative. Let B belongs to G, A plus B equal to B plus B. Obviously it is satisfying these commutative elements. Say example 2 plus 3 equal to 3 plus 2. Thus G plus is an abelian group under addition. I hope that is clear. Now let's check out the next example, that is example number 2. G is a set of rationals except minus 1. Binary operation star is defined by A star B equal to A plus B plus AP, so that it is a group. The first condition is for the closure property, that is, let A B belongs to G, A star B equal to A plus B belongs to G. Obviously it is satisfying the closure property. The next one is the associative property. We have let A B C belongs to G. We have to prove this associative condition. So if we take the left hand side, say A star B star C equal to A star using the defined condition, uh, B plus C, since A is taken, you will use C plus B plus C. A plus B plus C plus BC plus A, B plus C plus BC. If we simplify, A plus B plus A plus B plus C plus BC equal to A B plus AC plus ABC. This is for left hand side. Now for the right hand side, A star B star C equal to, using the define operation, A plus B plus AB star C equal to A plus B plus AB plus C plus C A plus B plus AB. Now if we simplify, A plus B plus AB plus C plus AC plus CB plus ABC, we see that both the left hand side and the right hand side are equal, so it satisfies the associative property. The next one is the existence of identity element. Let A belongs to G and E be the identity. The condition for identity element is given by A star E equal to E star A equal to A. If we use this one, A star E equal to A, using the defined condition, that is A star B equal to A plus B plus AB. Using this condition that is defined in the equation, in the equation, you will get A star E, A plus E plus AE equal to A. Now if you take E common, E1 plus A equal to, if we bring A to the left hand side, we will get 0. Now E equal to 0, which is thus E is not equal to -1. Thus identity element exists. Now next is for the existence of inverse. Let A belongs to G and A inverse be the inverse of A. The inverse condition is given by A star A inverse equal to A inverse star A equal to E. If we take this, A star A equal to E, using the defined condition, you will get A plus E inverse plus A inverse equal to, since the identity element we got in the above is 0, well, let's just substitute it as 0. And if we take if we take E common outside, 1 plus A will be left. Now if we bring A to the right hand side, you will get A minus A, next inverse minus A. Now if we bring 1 plus A to the right hand side, you will get 1 plus A. Thus the inverse element also exists. Now the group G star is a group. We have proven that the group G star is a group. That's all. Thank you.